All right, so to wrap up this section on titrations before the exam, I wanted to cover a last set of topics that I think will be useful to you. So we've introduced these topics, such as our initial pH, midpoint pH, and equivalence point, but I wanted to do an example where we sort of were able to calculate these based on information in our problem. So let's calculate our pH at those points in a titration of 50 milliliters of 0.01 molar sodium phenolate, as well as 1 molar HCl. Okay, so we know that we're titrating a strong acid into a weak base, and we know that it's into the weak base because the weak component is always going to be our analyte, so it's always going to be in our flask, and the strong component is going to be in our burette. All right, so that means that we are going to be concerned mostly with what's in our flask. Okay, so our starting pH is going to be based on our sodium phenolate. All right, so if we're trying to get our initial pH, remember that we haven't added any of our acid at this point, right? So if we haven't added any of our acid, that means we're not going to do a before and after table, right? So no mix, no before and after. Okay, so if that's the case, then we're just going to be solving a weak acid or a weak base problem. In this case, it's going to be a weak base problem. All right, so let's set up our weak base problem with an ice table. Right, so now we do our ice for weak base, which means we're going to have A minus plus H2O in equilibrium with HA plus OH minus, right? ICE. I'm going to skip the water. All right, now since we're dealing with an ice table, we know that it has to be concentrations. Do we have our initial concentration of our A minus? Yes, we do, because that's going to be, right, this is our A minus. It is the conjugate base of a weak acid. All right, so remember, this is a salt problem, so we'd be using our conjugate base, I'm sorry, our conjugate base of a weak acid, right? So in this case, we have 0.01, all right, and we started out with none of those, okay? Then we have 1 minus x, 1 plus x, and 1 times positive x. So we have x, x, and 0.1 minus x. All right, now I've given you the Ka for this. Is that what we would use here? The answer is no, because we have a base accepting a proton and becoming an acid. So that means that this would be the Kb. All right, now Kb is going to equal the Ka, or is going to equal the Kw over Ka. All right, which is going to give us 9.52 times 10 to the negative fifth, which is equal to x squared over 0.1 minus x. I'm going to skip some steps and say that x is equal to 9.76 times 10 to the negative fourth. All right. Now, x corresponds to my concentration of OH at equilibrium, which means that I can solve for my POH, which is equal to the negative log of my concentration of OH, so 9.76 times 10 to the negative fourth, which is equal to 10.99. So that would be, I'm sorry, no. Of course it's not that high, we're dealing with a base. So our POH would equal 3.01. And if we say that our pH is equal to 14 minus our POH, then that would give us a pH of 10.99, which is appropriate for a base. All right? Notice that for that, we didn't need our volume of HCl added. All we needed was to solve our weak base problem. Okay? The next thing that I want to talk about is our midpoint. Okay, so if we're looking for our pH at the midpoint, what is our midpoint? Well, if you remember from the last example, our midpoint is the point where we have an equal number, where our concentration of HA, rather, was equal to our concentration of A minus in solution, right? So that was our weak concentrations have to be equal, right? Not our concentration of strong, but our concentrations of the weak have to be equal, okay? And remember, that did something special to our Henderson-Hasselbalch equation, right? Because we had that being the concentration of base over our concentration of acid, all right? If those two concentrations are equal, then this becomes a 1, and this, the log of 1, is equal to 0. That simplifies our pH expression for the Henderson-Hasselbalch equation to just say that pH is equal to pKa. Well, pKa is equal to our negative log of Ka. All right, so we plug in our Ka there, and we see that our pH is in fact equal to 9.98 at our midpoint. Again, notice we didn't need any information about our volume of HCl added. All right? In fact, we didn't even need our concentrations for this problem. Okay, so keep that in mind. Lastly, if we want to find our concentration at the equivalence point, it might be a good idea to know what our equivalence point is. Well, our equivalence point was the point where our moles of acid were equal to our moles of base. Right? So let's start off by calculating our moles of something that we know. Right? We have a volume and we have a molarity. So that means we can figure out our moles of our phenolate. Excuse me. So that would mean that we would take 0.01 molar times 0.05 liters, and that would give us 0.0005 moles of our phenolate. All right? Now, if that's our moles of our phenolate, then that would have to correspond to 0.0005 moles of our acid. Okay? So that means that we need 0.0005 moles of H plus. Okay? And that corresponded to half a milliliter, right, of, let's say that we picked a volume, right, and we said, okay, let's pick, we know that that's our molarity, right, so we know that we are trying to figure out our volume of this, right, so that would give us, we would divide by, it would be 1.00 moles per 1 liter, right, all I've done is divided by my molarity, right, because we have an M1 V1 equals M2 V2 problem. Here is our M1 V1, this is our M2 V2. So what we're doing is we're actually dividing and we're saying, okay, if I want my volume 2, then that's going to be M1 V1 over my M2, okay? Or sorry, yeah, is that right? Okay, so this would give me 0.0005 liters, okay, or half of a milliliter. All right, so now we have enough information to set up our before and after table, right? So if we do a before and after table, because we know that the volumes, or sorry, we know that the moles have to be equal, right? And we have our moles of H plus, so we know H plus our phenolate is going to go to HA, right? So we have before change after. .0005. We have 0.0005. 0.0005. And remember, these are in moles, right? All we've done is just plug in our moles because we know that those have to be equal, right? And then we're going to subtract off. We know that we started off with none of that, okay? So we're going to subtract off our limiting reagent, which was 0.005, 0005, minus 0.0005, plus 0.0005, which means we're going to have 0.0005 as our concentration of HA. This will be 0, and this will be 0. All right? Now, if you remember, at this point, we can't use Henderson-Hasselbalch because we don't have both of those, right? So that means we have to set up an ice table. So if we set up an ice table, starting off with our HA, right? We know that HA is going to be in equilibrium with H plus A minus, right? Again, we're just flipping that around like we did in the last problem. All right. We know that we have nothing here, and we know we have 0.0005 divided by, right, because that's in moles, we're going to have to divide that by our total volume, right? So we know that our total volume, right, because we had a half of a milliliter here, so we added that to our total volume that we had here, right? So that would have been 50.5 milliliters as our total volume, okay, which corresponds to 0.0505 liters. So we would take 0.0005 moles, divide that by 0.0505 liters, which would give us 0.0099 molarity, 0.0099 molar. All right, so we would say 1 times negative x, 1 times positive x, 1 times positive x, right? So you get x, 0.0099 minus x, all right? And that would correspond to our Ka, right? So we have 1.05 times 10 to the negative 10 is equal to x squared over 0.0099 minus x. I recommend using your quadratic formula for this one. X is equal to 9.72 times 10 to the negative 7th. X corresponds to our H plus, which means that our pH is equal to 6.01 at our equivalence point. You should be relatively familiar with how to do all of this, all right? Because again, we've gone through several examples of the different conditions that you'll need, okay? So that covers these, all right? Now all of that was for slides 21 and 22, right? Because I've given myself a little bit of extra room to do all of these examples in the slides. All right, now I want to talk a little bit about what these titration curves will look like. Okay, as we've gone through them, right, I want to kind of recap for the exam a little bit. So we know that we're now on slide 23, because we skipped 22, because 22 was just space for me to work out those problems. All right, slide 22, so we're now on slide 23. Slide 23 is strong acid and strong base titrations. Okay, so we have strong acid, strong base. Notice that for these, right, what are they going to look like? Well, if our analyte, if that is the acid, right, then that's going to be in our flask, right? And if it's in our flask, that's going to be what we start with and what we measure in terms of our pH, okay? So if it's the acid, it's going to start at a low pH, okay? We are then going to be adding in a volume of base, which will make it more and more basic, okay? So this would be volume of, say, sodium hydroxide, and then this would be our pH, okay? These are going to have an equivalence at 7, okay? On the other hand, if you started out with base as your analyte, okay, then this would be like volume, let's say, of HCl, okay? So again, your pH. The analyte is what you're going to start with as measuring, so that's going to have a high pH because it's going to be basic. And then as we add more and more acid, we will become a lower and lower pH. All right? Again, our equivalence point will be 7. Okay? Now, what about if we have a weak acid and a strong base? Okay, well, if we've got a weak acid and a strong base, now we are on slide 24. Okay, here, what's going to be in our flask? Well, we know that our weak is going to be in the flask because the weak is the analyte. So that means that it's going to be our weak acid. Okay, so if it's our weak acid, we're going to start at a low pH. Okay, and then over time, as we add more and more strong base, we will reach some equivalence point. Okay, but there must be a buffer region. Okay, so this will be a buffer region. And it's going to be a buffer region because our analyte is weak, right? So it's going to be creating an environment where it shifts back and forth to reestablish the equilibrium. Okay, so this will be a buffer region at the beginning. Okay, now, then we will go into our equivalence range, right? Our equivalence point will be somewhere in the middle, okay? But it may not be at a pH of 7, all right? And that's because as we are adding it, like if we add an equal number of moles of acid and base, then once we've done that, we have to establish our equilibrium. And once the equilibrium happens, this will end up being a little bit higher because we're dealing with a conjugate base that's going, we're dealing with a conjugate base that's going to pull it even more basic than it was before. All right? Then afterwards, after our equivalence point, we will have an excess of, let's say, OH minus, since we're dealing with a strong base. And I'll just say that my strong base was like my volume of sodium hydroxide added. Okay? Notice again that this is not at 7, but will be a little bit higher. Okay, now on 25, this is going to be for our weak base, titrated with a strong acid. Again, since the weak component is the analyte, right? It goes in the flask. So that means that our weak base is in the flask. All right? So if we were to plot this, what we would see is that we know that we have a weak base. So our pH is going to start out relatively high, right? There's going to be some sort of buffer region. All right? Because the weak is going to be buffering itself, right? And then as we add more and more of our strong acid, right, so that would be like our volume of HCl that we've added. So as we add more and more, right, we will reach an equivalence point. All right. And that equivalence point will correspond to a pH that is lower than 7. So say something like 6. Now, why would it be a pH lower than 7? Well, we started out with our weak acid, weak base. So if we put in an equal number of moles, we started out with our weak base, right? So if we put in an equal number of moles of strong acid, once all of that is used up, then we're left with our conjugate acid of the weak base. And then when that is allowed to shift back to equilibrium, it will make our system slightly more acidic. All right? So that would give us a lower pH. Okay, so again, pH for a weak base strong acid is going to be less than 7. and the pH for a weak acid, strong base is going to be greater than 7. Okay? All right? Now, how are we going to tell when we have reached our equivalence point? Well, as I talked to you guys about at the beginning of this chapter, right, we can use something like an indicator. You guys are pretty familiar with that after your phenolphthalein experiment last semester. Okay? Remember that, and this would be our next slide, which I'm not sure, I think it's 26. All right, so slide 26, right? We have this cool plot, right? Where we have all these little Erlenmeyer flasks. Okay, this one in the middle is that light pink. It's the balance between the dark pink for a basic solution, okay, and clear and colorless for our acidic solution. At the equivalence point where we have an equal number of moles of acid and an equal number of moles of base, our indicator will tell us as soon as our system becomes basic, right? Or if you're using an acidic indicator, it will tell you when it flips back, okay? So in this case, right, each of these will have a different set of ranges. You can see the pH ranges of common indicators on that next slide, which would be slide, and not slide 27, but slide 28. Slide 28 shows you a whole bunch of indicators. Notice that some, or rather that they're all useful at different ranges. So some may be useful, for example, crystal violet. That indicator is useful for the pH range from 0 to about 1.9, all right? Whereas something like bromethiol blue that's useful at a pH range, it looks like, of 6 to 9. All right, so you wouldn't want to use crystal violet if your equivalence point happened to be somewhere around 7. All right, each one is going to change a different set of colors and is going to have a different equivalence point. All right, and you'll get to use a whole lot of these when we do the experiment either in lab or later when you get to another one in quant. All right, but the whole point is, right, indicators are very useful at helping you determine where your equivalence point is, and from your equivalence point, that will tell you how much acid you needed to add, how many moles you needed to add, and how your system reestablished equilibrium. All right? Now, another way to determine the endpoint is to use a pH meter. All right, so your ways to determine your endpoint or your equivalence point. You have a pH meter or you have an indicator. All right, so with that, we've covered all of our topics that will be on the exam. I'm happy to answer any questions for you guys, and I will have Zoom interviews, or not Zoom interviews, I will have Zoom office hours for you guys, so that way you can ask me any questions that you need. All right, good luck.